Hi, my name is Johan Tekel, and today we want to solve an exercise about plane stresses. So I'm basically gonna draw the situation we're gonna have. Here's a body, an infinitesimal element with the following given stresses: 40 Newton per millimeter squared in the. Okay, I'm gonna draw the coordinate system later. So let me draw the coordinate system. It's this one. The x-axis going to the right and the z-axis going downwards. Okay, and we've seen together already that when we use this coordinate system, the angle phi is defined clockwise as a positive angle. This is the rotation angle for phi when it's positive from the x direction towards the the z direction, kind of. Okay, so the normal stresses are given. In the z direction we have 40 Newton per millimeter squared, and in the x direction we have minus 100. You see here is actually a compressive stress that we have there. Is directed inward. Okay, of course we could also draw those stresses going outwards or on the positive x face going in the positive x direction, and the negative on negative x face going in the negative x direction with minus 100. We could do it that way. We could draw it that way. Yeah, so that's actually the current state, and given is also a specific cut of that body under a given angle psi, and psi is 30 degree. So here are the given values. We have sigma x already that we can see here. It's minus 100 Newton per millimeter squared. We have sigma z given also with 40 or plus 40 Newton per millimeter squared. We have, I haven't drawn it yet. We have the shear stresses tau xz given with 50 Newton per millimeter squared. So how do we draw them? On the positive x face in the positive z direction. So here it's going downward. So you always need to pay attention to the coordinate system that's given. Okay, we've seen that. I'm going to put the link of the video in the description too. You need to pay attention to the coordinate system you have, and depending on which coordinate system you have, those shear stresses might be defined differently. But the main idea is on the positive face of the considerate axis. So for example, here on the positive z face, and the shear stresses are positive in the positive x direction. So on the positive z face is down here in the positive x direction, so to the right. That's how the shear stresses will be distributed here, and in this case they're positive with plus 50, so I don't have to change anything. That's already the direction. If we had here the value minus 50, we would have drawn it in the opposite direction, or we could still have drawn it this way and just and could have written here minus 50 instead of 50. Okay, so we're basically done here with the drawing, and let's start with the calculation. So what are we looking for? We need to compute the principal stresses. Oops. sigma 1 and sigma 2. We also need to find their directions. So principal stresses and principal directions. This is actually how it's called. I'm gonna check it, but basically, on in which direction do we actually find those principal stresses, sigma 1 and sigma 2? We might actually compute the maximum shear forces too, tau max. And what else? Okay, that's basically for the first part. And then we need to figure out which stresses do we have in this cut here. Okay, so the second part is basically gonna be stresses along, or let's just say in the cut. I want to say along the cut, but whatever. The cut, you can call it CC. Along the cut, CC. So which stresses are we gonna have if we cut this element under this angle 5 on 30 degree? And yeah, so let's start with the calculation. We can solve this exercise, of course, with the Morse seeker if you want. I'm gonna solve it here with formulas though, so that we don't need to draw the circle and make sure that we have the right measurements and stuff like that. So I'm just gonna do it with formulas. Okay. Yeah, so let's start. How do we compute the principal stresses sigma 1 and sigma 2? We basically have formulas for that. Sigma 1, we can also do that with the circle, but the formula can actually be derived from the circle too. So sigma 1 is the sigma m, sigma middle, the mean value of the stress. So what is it? It's sigma x plus sigma y divided by 2. First, we get to the mean value, and then we add the radius. We add the radius for the biggest value, sigma 1, for the smallest value, sigma 2, for the smaller value from the 2, basically, we're gonna subtract it. So sigma 1 is with the plus and sigma 2 is gonna be with the minus here. And what we subtract is basically the radius. Okay, you might not understand what I'm explaining right now, so I will basically recommend you to watch the video where I explain the theory behind all this. So this is just an exercise I'm just solving using the formulas, basically. And when you know where the formulas come from the circle, basically, it's kind of like easy to come up with this, to write it and to basically memorize the formula. Okay. Right now, I just have this small circle in my head, kind of. Really, a random circle, it doesn't really matter. The middle will be here. So first we need to go to the mean stress, sigma m. And from the mean stress, the mean value, sigma m, m for middle here, or for mean, middle, mean value, we need to add the radius. Okay, and how do we compute the radius? If we take like a random, okay, I didn't want to draw this. I actually didn't want to draw it, but yeah. Now with this circle, I can't draw it anymore. But let's say it's just a random state, and it's completely random what I drew here. This circle is not this case. Okay, it's not this state. It's just a random one. Let's say that we have a sigma x here and a tau xy. I'm using xy here. Let's say xz. It doesn't matter. And then a sigma y here, for example, and a tau xz minus negative. Okay, so this is the state. If we want to figure out what's the maximum value sigma 1 over here, what do? First, we come to the mean value by doing sigma x plus sigma y divided by 2. That's the mean value. And then we need to add the radius. And what's the radius? The radius here is the same as this distance here. Okay, this one. And how can we compute this? We can use Pythagoras to compute it. this length squared equals this side here squared plus that other one also squared. What's this side over here? This one? That's tau xz. And what is this one over here? That's basically sigma x minus sigma y. Then I have this difference here between the two divided by 2. So I just have this one. Okay, so sigma x minus sigma y divided by 2 squared, oops, then plus tau xy, tau xz in this case, sorry, I say sigma x minus sigma y, I meant sigma z. Okay, so sigma x minus sigma z divided by 2 squared plus tau xz squared under the square root. Okay, so you can do it with the sec or you can do it with the formulas. Okay, I'm not gonna try to demonstrate or to prove where the formulas are coming from anymore. Otherwise, we're gonna lose a lot of time here. So let's just input those values in the formula. What do we get? Minus 100 plus 40 divided by 2 plus minus square root of minus 100 minus 40 divided by 2 squared plus 50 squared under the square root. Let's put it in the calculator. So minus 100 plus 40 divided by 2 mean value plus square root of minus 100 minus 40. We could put directly minus 140 at that position, but yeah, plus 50 squared under the square root. So this one is sigma 1. Okay, 56.02. The exact value is this, is minus 30 plus 10 square root of 74. Let's write it first. So sigma 1 equals minus 30 plus 10 times square root of 74. Oops, 74, not 44, equals 56, yeah, 0.02. And Newton per millimeter squared. And then sigma 2 is what? In the same formula, instead of adding the radius, we are at the mean value. Instead of adding the radius to come to sigma 1, we subtract the radius to come to sigma 2. Okay, so here in my input, I'm just gonna, where is it? It's over there. I'm just gonna remove the plus over here and change it to a minus. And that's my sigma 2 value, minus 116.02. So sigma 2 equals, in engineering mechanics, we define sigma 1 as being bigger than sigma 2 with respect to the sign. So in this case, 56 is bigger than minus 116. Okay, there are other subjects where we will just consider the absolute value and we would say that this value is bigger. I mean, we consider the absolute value and we will call this one sigma 1. But in engineering mechanics, this is sigma 2 because it's smaller with respect to the sign. So the actual value is minus 30 minus 10 to the square root of 74. And that's approximately equal to minus 116.02 Newton per millimeter square. Okay, that's one part of the first question. We still need to find out the principal directions. So, which rotation do we need to apply to the current system? And this is the x-axis. Which rotation do we need to apply to the current system to reach the state where the stresses, the normal stresses are this big, are the principal stresses. So where sigma x will become sigma 1 and sigma y will become sigma 2. There's also a formula for that. Tangent from 2 phi x equals, what is that again? We can basically figure that out here from a random cycle. This is randoms, Morse cycle. Huh? This is not the Morse cycle related to this exercise. It's just a random one. The rotation that needs to be done to reach the principal stresses is this one. And how can we define it? And we also know that in the Morse cycle, the angles are doubled. That's why we have 2 phi here. Because in reality, it's just going to be phi, but in the cycle, it's doubled. So tangent 2 phi equals what? You see here, the opposite side is going to be tau xz basically, and the adjacent side is going to be this one, from sigma middle to sigma x. And we've defined this length before, right? It was sigma x minus sigma z divided by 2. So tangent 2 phi is opposite side tau xz divided by adjacent side, this value. So I can put the 2 on the top at the numerator, and we get this sigma x minus sigma z. You see, I'm not looking at those formulas in a book or something like that. You can actually, it's not really like memorization. I mean, you can memorize them. They're also pretty simple to be memorized, but you can actually understand them and write them down, like, yeah, as we're doing right now. So this is tangent 2 phi. And what we're looking for is phi. So phi asterisk basically is going to be what? We're going to use the inverse function of tangent. So I equals tangent or tangent minus 1, like it's written on calculators. 2 tau xz sigma x minus sigma z. And this will be 2 times phi asterisk. So I'm going to divide this by 2. This would have been 2 phi asterisk equals tangent minus 1, blah, blah. So this is what we need to input in the calculator with 1/2 arc tangent or tangent minus 1 from 2 times tau xz, what is it? 50 Newton per millimeter squared, divided by sigma x, what is it? Minus 100 minus sigma z, what is sigma z? Plus 40. Okay, need to input this. Let's go. 1/2 times tangent minus 1 from 2 times 50 divided by minus 100 minus 40 equals minus 17.76. So minus 17.777. I'm going to save this value in A. So now what's the problem? I mean, why is there even a problem? We've just figured out the following. Here's our current state with x and z. Okay, very important. Phi is positive from x. Is the rotation phi. Okay, is positive, defined from x towards z. So in this direction, clockwise. So we figure out with this calculation that if we rotate the current state with an angle of minus 17.77 degree or minus 17.8, so if we just do such a rotation, not in the positive direction but in the negative one with 17.8 degrees, we reach such a state Okay. Okay. And those directions, this direction, a direction in math is not just like an orientation. It's not just from left to right. No, a direction in math is like a whole line. Okay. So we just figure out that if we have this rotation from 17.8 degrees, our currency will become this one. And either this direction or the other one is gonna be a principal direction. So is this direction that we just switched, is it direction 1? Is it like the direction for sigma 1? Or is it the direction for sigma 2? We don't know. And the other one, is it like sigma 1 or is it sigma 2? We don't know that either. Okay? This is what we know. If this direction is sigma 1, then 90 degree to this direction, we're going to have the direction for sigma 2. But if this one is sigma 2, then the other one is going to be sigma 1. But we don't know yet if this one is sigma 1 or sigma 2. So we need to figure that out. How do we do that? We use our transformating formulas. We have formulas that allow us to rotate the coordinate system with for an angle phi. They look like this: sigma x plus sigma z divided by 2 plus sigma x minus sigma z divided by 2 times cosine 2 phi plus tau xz sine 2 phi. Okay, this formula might look different than the one you used to. Okay, there are different ways to write this formula. You just need to pay attention to the fact that sigma 2 phi is 2 sigma phi times cosine phi. And you also need to pay attention to the fact that cosine 2 phi is cosine square phi minus sine square phi, which by the way could be rewritten as cosine square plus sine square equals 1. So cosine square minus 1 will be minus sine square. Yeah, so it could be rewritten as this. Okay, just keep these formulas in mind. If you keep these formulas in mind, you can figure it out. I mean, there are different ways to write this formula. This is the one I have in my head, but I also know the other forms from the same formula. And knowing this, you can figure them out. So we're just gonna what are we gonna do? Okay, we're gonna put the angle phi, this angle that we just found in there, that we just calculated. We're gonna put it in here and compute the stress that we obtain. Okay, what does this mean? We take the sigma x that we had and we transform it, we rotate the coordinate system with this angle. And we're gonna find a value, right? Which value are we gonna find? We expect to find either sigma 1 or sigma 2. And we know those values already. So if we find sigma 1, then we know, this one is sigma 1 and the other one is sigma 2. If we find sigma 2, then we know, okay, so this direction is for sigma 2 and the other one is for sigma 1. So let's just input those values in here. Sigma x is minus 100 plus sigma z is plus 40 divided by 2 plus sigma x minus 100 minus sigma 2. Okay, so minus plus 40 basically, that's what's happening here, watch out, divided by 2 times cosine 2 times, watch out, the angle is negative, minus 17.77, let's put it like that, but we save it already in the calculator, so we're going to use the full value, plus tau xz, that's 50, plus 50 times sinus 2 times the angle again, the minus 17 plus 17,77, blah blah. Okay, yeah, we just Oops, you just need to put it in here. Minus 100 plus 40 divided by 2 plus minus 100 again minus 40 divided by 2 times cosine 2 times a. We save it before in a. The angle 17.77 and whatever. Okay, it's saved in a, plus 50 times sinus 2 times the angle again. There we go. Minus 116. We find minus 116,02. And what is this? This is sigma 2. Right? We calculated before. So what does it mean? That means that this direction is not sigma 1. What is it? It's sigma 2. If this direction is sigma 2, which one, if this direction belongs to sigma 2, which one belongs to sigma 1? The other one. Okay? So what does it mean? I'm just going to write it here. Oh, this way. Ah, man. What does it mean? We had this state, this stress state. Ah, it's set going downward. Like this. Okay? We rotated it from an angle of 17.77, let's say, degree. Okay, that's the negative direction. The positive direction would be clockwise. We reach this state, this inclined state, and this stress that we have in that direction is not sigma 1 but sigma 2. It's sigma 2 equals minus 116 Newton per millimeter squared, and the stress in the other direction, 90 degree to this direction. So it's in both ways. It's the same direction, sigma 2 equals minus 116. And 90 degrees to this direction, we have sigma 1 with the value that we computed already, 56.02. Sigma 1, 56.02. Yeah, I can write the O2 here if I want or not. 56 is enough. Okay, so it means that this angle, the phi asterisk that we had with minus 17.77 is actually phi asterisk 2, leading to the direction where we have sigma 2, the principles for sigma 2. Okay, so this is phi 2. We rotate from the horizontal to this state here with phi 2 asterisk. How do we get to the other direction? Phi 1 asterisk is simply phi 2 plus or minus 90 degrees. Like X and Z, they always have 90 degrees between each other. Even in the Morse cycle, you see sigma 1 here, sigma 2 over there. What is it in the Morse cycle? It's 180 degrees. And we know that the Morse cycle has every angle doubled. So in real life, it's 90 degrees between the two. So if this is phi 2, we can say that phi 1 is what? So from the horizontal to this direction over here, what is it? It's phi 2 plus 90 degree, okay, or phi 2 minus 90 degree. Now this rotation, the angle I'm drawing right now, this one is not in the assumed positive direction for phi. Okay, so if I want to consider this angle here, it's going to be minus 17.77 minus 90. If I want to use this angle, this is going to be minus 17.77 minus 90. And it's going to be minus 17.77. We have that angle already in A, right? Minus 17 point blah blah. Okay, minus 90. It's gonna be minus 107.7. As you see, minus 107.8. I'm just gonna say, but that's quite a big angle. Why would we use this one if we can just use this other one here, right? We can just use this one. How do we come to this one? It's phi 2, so the negative value here, as we said, we can add or subtract 90. Okay, if we do, I'm just gonna write the both values here. Phi 2 is what? Minus 17.8, let's say. And if we subtract 90, then we get that value we just had, the 107.8. I mean, this was an approximation, but the 107.8 negative. But if we add it, we get the A plus 90, we get the 72.23, basically. Okay, 72.23 degrees. Okay, in the positive direction of x-z. Okay, so this one is 72.23 degrees. So this is like an alternative way to come to that. What else? If we want to compute the direction for the maximum shear stresses, we just need to add or subtract 45 degrees from this angle. So from the 17.77 that we have already in A here, we can just add 45 degrees and we have 27.23. That's the angle for the maximum shear stresses, and we need to rotate positively with 27.23, or we can add 45 again. We can just add 45 the number of times that we want, doesn't matter. This is also one of those stresses and those directions for the maximum shear stresses. Or I can subtract it again. This was the original value. I could subtract 45 minus 62.76, and it's also one of those directions. So if these are the principal directions for sigma 1 and sigma 2, the directions for the maximum shear stresses, just they lie basically 45 degrees to this original direction. So those two here are the directions for the maximum shear stresses. So from the principal stress here, that's sigma 2. This was sigma 2, right? Where is it? This one. Yeah, this is sigma 1, this is sigma 2. From sigma 2, we can add 45. That's the direction. Okay. If we add 45 again, we come to this principal stress, but then we add 45 a second time, and we are again on one of those directions for the maximum shear stresses. Okay, so those are the two possible directions for the maximum shear stresses, and here are the two directions for the maximum normal stresses. Okay, good. So principal stress is sigma 1 and sigma 2, and then with principal direction we got it. Now the stress in the cut CC, let's do that cut. So what happens now? We have this situation here with X and Z. But then a cut is made over here. So now we want to know what happens if a cut is made here. A cut along this line is the same as having a body that has this position, that basically has this position here, okay, where this side is parallel to the cut, okay, it's the same stress state. So having a cut there is basically the same as just rotating the original state. So what we need to consider here though is the angle. We know that we have an angle of phi with the horizontal, and phi is given as 30 degrees. So this is like 30 degrees. And we just need to figure out how do we need to rotate this system to get to this state. Okay. So basically I want the x-axis now to be, I want this side here, or this one, doesn't matter. I want this side to become this one, or the left side to become the upper one. Okay, so basically I want my x-axis that's currently or originally horizontal to become this direction here. How do I do that? I can just draw it here. This is the direction I want to have, I want to reach. And what was the original direction? The horizontal. X was just horizontal. Okay, and I need to figure out which rotation happened here. This one. Or you can also draw it here. This one. Now, what's this angle? That's what we need to figure out right now. Yeah, that seems to be 60 degrees. Look, between the horizontal, we have the horizontal here and this inclined line, yeah? And between the two, we have 30 degrees. So that means we also have 30 degrees over here. By the way, this is geometry. There are like 1,000 different ways to do this. So you can do it in a different way. We have 30 degrees over there. And this angle here, this line, I draw it exactly so that it will be perpendicular to this side. Because we want the same way as the x direction is perpendicular to the x face, kind of this direction that we want you to reach, we can call it psi, needs to be perpendicular to this face here. So it's a 90-degree angle that we have here. And in this small triangle, the sum of the angles should be equal to 180. If you have 90 already over here, the sum of the other two needs to reach 90, needs to be equal to 90. 30 is already present here, so the angle we're looking for is 60. Okay, you can do it in different ways. So the rotating angle we're looking for is 60. So phi is 60 degrees. It's 60 degrees in, yeah, 60 degrees clockwise. Okay, so it's positive. It's basically plus 60. Very good. So we're just gonna do that transformation with the same formulas. We're just gonna input sigma psi for phi equals to 60 degrees, and we're just gonna compute it. So it's the same formula that we use here, but now the angle is not, what was it here, the 17.779 is not the phi axis anymore. Now it's 60. So minus 100 plus 40 divided by 2 plus minus 100 minus 40 divided by 2 times cosine 2 times 60 plus tau xz, that was 50. Really? Yeah, 50 times sinus 2 times 60. And we can just put it in the calculator. Minus 100 plus 40 divided by 2 plus minus 100 minus 40 divided by 2 times cosine 120, 2 times 60, plus 50 sinus, oops, that's not sinus, sinus is here, sinus 2 times 60. Well, what? That's huge, like too big. Ah, look, I have a square here for no reason. Okay. There's also that this position here where I didn't press the button sinus, but I pressed something else. Did it change anything? No, I think this should be good now. 5 plus 25 square root of 3, 48.3. Sounds plausible. And we know, okay, look, why did I also say that it's too huge? We know the maximum stress is already 56.02 and minus 116. So if we get 800 or whatever we just got there earlier, we know that there's a mistake. I also knew that I had put something wrong, but I didn't know I had the square, but you saw it too. The square was definitely a wrong input there. So 5 plus 25 square root of 3 equals approximately 48.3. That's the normal stress under that state, under that cut. Should I draw it there? Don't know. I'm gonna draw it here. So we basically did a rotation from phi equals plus 60 degrees. Okay, and we get a sigma psi equals 48.3 over there. What else can we do? We can compute also the sigma. Actually, when we talk about this cut, the cut that was made here, okay, we want to know the stresses perpendicular to that cut and the shear stresses. So the shear stresses are definitely to be computed here. The formula for the shear stresses, tau psi eta is minus 100 minus 40 divided by 2 times sinus 2 times the angle plus tau xy 50 times cosinus this time 2 times the angle. That's the value for tau, and that's the value for, I don't really think it's very necessary here, but we can compare it to the value for sigma eta. Sigma. Okay. We're working with x and z here, so we're not gonna use psi. That's kind of like the equivalent of x in the Greek alphabet. We're gonna work with zeta. It's like the equivalent of z. It's just later over here. But it's just those are just letters. Just names. Doesn't make a value wrong or right. Those are just names. Oh man, sorry. I'm really confused here. X is there, so it's actually psi, but what needs to be replaced is eta. What I called eta here needs to be replaced with zeta. Oh man. So this one is tau psi for x, kind of like after the rotation, and then that zeta. Psi zeta. Good. Yeah, so I'm just gonna input this, and I'm also gonna compute sigma zeta, as I said. Sigma zeta is pretty similar to this formula. We're just going to put a minus over here and minus there. So that's the first thing I'm going to do. I'm just going to put minus here. Oops. Here, not a plus, but a minus. And then in front of the shear stress, we're going to put here, not a plus, but a minus. The value is minus 65 minus 25 square root of 3 is minus 108. So minus 65 minus 25 square root of 3 equals minus 68. minus 108.3. Here sigma theta equals minus 108.3, so it's basically compressing minus 108.3, and then the shear stresses, what did we say, minus 100 minus 40 2 times sinus of 120 plus 50 times cosine 120 minus 25 plus 35 square root of 3 equals approximately 35.62 Newton per millimeter squared. So here is psi, here is theta. Positive shear stresses are on the positive psi face in the positive theta direction, so like this, and they're in the opposite direction, and here positive theta face in the positive psi direction, like this, and there like that, with the value 35.6. Good. We haven't computed the maximum value of shear stresses. So the maximum shear stresses, we can do that. It's basically, the maximum shear stresses are basically equal to the radius. When we put it vertically like this, we're gonna reach the maximum shear stresses. The radius equals the maximum shear stresses. So this value here in the brackets, what is it? 10 times square root of 34. That's our max. 10 times square root of 34 equals 86.02 Newton per millimeter squared. Very good. So we basically did everything that we had to do here in this exercise. So thank you for listening. If you have any questions, you can just use the comments below, and I will be happy to answer them. See ya.